Okay, we'll try to keep within time. We're team 2, also known as Simple G. So team 2 looked at the impact of heat stress on global, local, regional food systems. More specifically, we're interested in understanding how the true impact of heat stress will have a cascading and multi-scalar effect across our food system, because our food system is so interconnected. Now, from the literature, we understand the IPCC report scenarios tell us that climate stresses like changes in temperature, sea level rise, changes in precipitation will all have a varied and adverse impact on our food system. And these are usually measured in terms of changes in yield. Some places will win, some places will lose. The science on that is kind of fuzzy. There'll also be reduced resource availability. That means land, water, and other inputs in some places will be easy, in other places will not be as much. And so that means there might be shift in where we grow our food. And then when we have these conversations with researchers and practitioners about what do we do? How do we adapt our food systems so that we're continuing to produce the food that the world needs to eat and be food secure? The conversation happens at 2 levels. They can be aggregated at farm level. So what will the farmer do? And usually that conversation goes something like, oh, we'll build a shed with air conditioning so cows are comfortable. One example. There are other examples, but they're kind of like that. Or system level adaptation that talks about, we'll change the financing of the system. We'll change the technological aspects of the system, which means, okay, so pecans won't be handpicked, cotton won't be handpicked. We'll mechanize that, which has already happened. But all of these conversations that are happening talk about the farmer and doesn't actually talk about the people who are in the field growing, harvesting in those conditions. So all of these adaptations actually miss this key component of our system that actually produces the food. So our research responds to this gap, this really, really critical gap in the literature, and asks, so what is the true impact of heat stress on farm labor? And what will be the multi-scalar, local, regional, global impact, cascading impact of those labor impacts on the system that is theorized in economic theory by this isoquant curve that I won't go into today, because that's a week's worth of lecture. Specifically, we look at the impact of one critical agricultural region in the whole globe. California is the 4th largest economy, can exist on its own as a country. As the largest agricultural producer in the US and probably in the world, produces over 3/4 of our food, both in terms of what we eat and also exports. So a really key area. And so if we shock this one region, what will that mean for the rest? So that's what we're interested in seeing. So this is our workflow. And we were lucky, a lot of the key components of our work was done before we got here by the team at Purdue, who aggregated and collected the global level data, both the global and the US level data, and built the Simple G database that we use in the second part to code our endogenous and exogenous components of this model that I just explained, to which we introduce 3 different climate shocks: heat stress, climate, and water, that's built off those papers that are in the text box on the side. And we ran 7 different scenarios to distill the true impact of heat using this GEMPACK software, also designed by Purdue University. We extracted the data in R and ran visualizations, analysis, and interpretations, which Andy will now take us into.
Yeah, thanks. And so we have 3 stresses that we're hoping to add to the agricultural system, and we're able to see how it responds. And if we visualize these quickly, we have the yield loss to climate change, the impact of heat stress directly on labor, and the reduced water availability. And so we're able to add a combination of these one at a time or all of them together to simulate how agriculture will respond by 2050. So we have a baseline scenario where we just add increase in population and these socioeconomic changes, but then we can add these climate shocks and we can apply these to the model and see how it responds too. And so our ultimate goal is to apply a shock to a certain region, so California, and then see how it cascades and impacts agriculture just in California, on the agricultural system in the United States, and using the simple G model, we can see how that impacts agriculture worldwide as well. We'll just present results here today where we just apply the impact directly to the entire continental United States, but future work will explore some of those other kind of administrative units. And so what we're able to do by running several different model formulations, we can run models with climate impacts, water impacts, and heat impacts, and we can run baseline scenarios and we can mix them and match them. And when we find the difference between those, we're really able to isolate the impact of heat stress on labor directly in the context of these other climatic changes that we know are going to happen by 2050. And we perform this within the simple G model, and the outputs are available at the grid cell level. Normally these aggregations are done at the national level or the state level. Here we have some regional analytics where you see the biggest decrease in labor productivity in this basin region in the Western United States. But when we aggregated this unit, so it really masks some of the variability at the grid cell level. You can see Southern Texas, which was from the previous heat stress map, is really the hotspot of where heat stress will impact agricultural labor. Doesn't really show up when we aggregate this by the region. And so we're advocating for this kind of grid cell level approach, this more detailed spatial approach to understand how these impacts will manifest. We can also look at the impact of heat stress just on crop output. If you change one thing in the system will respond to kind of perform this equilibrium, this balancing act, where we are able to provide enough food for all the people within the system. And that will change, obviously, labor use, but also crop output. And we can see, again, the same kind of region is impacted fairly heavily. We have the largest reductions in the kind of Mississippi Plain area, and actually some increases in crop output within this basin region. But again, this aggregation isn't as useful as seeing kind of the grid cell level detail. And finally, we can estimate how cropland use might change within 2050 with this additional heat stress. We can see how this varies spatially. And again, it's that kind of southern United States region, southern Texas and Florida will have the kind of largest change in cropland use. And so we're really trying to emphasize the importance of capturing the spatial variation at the local community level, where farm workers are in the fields, they're picking crops, and they're really engaged in agriculture. So when we're trying to implement adaptation strategies, we want to be able to do it at the finest resolution possible. But when we're using data that's at such fine scale, it brings up a lot of ethical concerns. And so I'll hand back over to my colleague to dig into that a little bit more.
I'll just add, if you're wondering what happened to California, we ran the model, we ran out of time to interpret it. So it's part of our future work. So if you look at that tractor, it captures all the keywords that went into our Dion checklist in terms of our responses to the elements we thought were critical to how we use this data. And three things stood out for us, which was collection bias, assumption of homogeneity, and unintended uses. So as I stated, our data was collected at very high resolution by global entities over which we have no control. And as a result, it was aggregated. Let's say labor. Labor is a singular representation of all the diversity of labor, right? It doesn't break it down into sex and age and ethnicity, which is really important because heat has differential impact by sex and age. So women who are 60 suffer different types of heat stress versus 25-year-old women, and heat stress between men and women, and by the way, children that are employed in labor are very different. But all of this is lost when we're modeling at this high level. And so that collection bias plays into that assumption of homogeneity. And there's a lot of downstream issues with that bias that we can't really mitigate. but we recognize and are cognizant of and reflect in the kinds of elements that Andy was talking about, the need to reflect our results back at the very local level, and then to design adaptation measures based on our locale conditions. And the unintended uses, when receiving regions see labor is going to move towards them in the future, and those receiving regions in the basin region, for example, if they don't want that to happen, they might preemptively put in place policies that reduces labor mobility. So we recognize this could be a potential adverse impact, unintended use of our data. And we do implore anyone looking at this paper in the future when it's published, Zhan, to really have a conversation with the researchers to understand the bigger results in the context of where they are before policy is made. And finally, just wanted to reflect on our journey. When we began this journey on Monday and Tuesday, the economic theory was a little, over our head. GenPack was all new. We weren't quite sure what we were coding or how we were coding, but we got the hang of it. We have this great team here, great camaraderie. We all just, divided, conquered, produced. We got some fuzzy data. We had some Mac compatibility issues. We're working back and forth. Even last night, I was like, oh no, that's the wrong data on those slides. And Elaina just cleaned that and used the right data. So anyways, that's us. And if you want to look at the visualizations, that's the QR code. Thank you to I-GUIDE and all of you.